So, a few things about myself. I am Italian. I hail from Ireland these days, where I work with my company. I have a background in physics and data science, and then I hopped into machine learning and AI for a few years. And I have quite a few hobbies and quite a few interests when it comes to technology. I mainly program in Python and Go, but I also dabble in Kotlin, Scala, and a few other technologies. And seriously, a lot of hobbies: mountaineering, hiking, martial arts, photography. I'm a bit weird. But enough about me. Who are we as a company? Our company is called Flow. We work mostly in the e-commerce area. We were founded in 2015, so we're not that old. There's about 50 people in the company, and we have two main areas of operations, namely Hoboken in New Jersey and Dublin in Ireland, which is where I work. And what we do is we provide a platform for people to turn their company into global e-commerce. And we do this because global e-commerce is a huge market. It's estimated to go to about 1 trillion by the year 2020, and it's experiencing a 23% year-on-year growth, and it represents almost a third of the whole B2C commerce. So it's really huge. And we do this by providing our customers with tools to overcome some of the main difficulties in global e-commerce, which are mostly localization and the automatic calculation of taxes and duties, which is a very hard problem. And just by doing this, most of our customers have experienced a very high increase in sales and revenue. We're talking about 30 to 50% increase in revenue. And for some of them, we unlocked over 100 new markets. And some of them also experienced increases in sales of even 70 to 80%. So it's really mostly about making everything easier for the customers, because the main problems for most of the people that do global e-commerce is that it should be easier than what it is. And sometimes it's really just annoying. Anyway, back to us. I mentioned I'm going to tell you a story, and any good story starts with a knight. We are the knight in shining armor in the story. Us data scientists, data analysts, programmers, us. And as any good knight, we have to defeat a dragon. And just a bit of spoiler here, it's not a physical dragon, it's just a metaphorical one. Namely, in data science, most of the times, my dragon is this. When from the board of directors comes a directive going like, oh, we have all this data, we need to use it. And you might, go like, how? To do what? It doesn't matter, just use it. Has that ever happened to you? Please raise your hand. Quite a few. And this is what happens. This is a result of a real life project I was working on. And what you do when you get a data set that you know nothing about. You just start poking around, see what's in there. So it's basically some EDA. So the first thing you do is open up a Jupyter notebook, import pandas, load the data, and start playing around. And this data set, what happened now? Better. This data set was actually quite big. It had over 850 features and 100,000 rows. So it's not that big, but if you know nothing about it, it's a problem. And these were the feature names. No word of a joke. This is actually what I saw. So what do you do then? I mean, what do you do except for hitting the bar? Has any of you ever felt like this? You just have too much information and you have no idea what to do with it. You don't know what's relevant. You don't even know what you're trying to do. You just have data. And the sad truth, actually the epic truth, is the fact that out of all information, when you have a problem to solve, this is what you need. Only a fraction of it. How do we find it? How do we determine what it is? That cursor is really annoying. Well, there are many ways to do that, and you should really investigate them, because having too much data and not knowing what's in there can lead to a lot of problems. It can lead to the fact that you don't understand what's in there, and you might miss the point. You might have, if you're training machine learning models, you might have too much time on your hand. It might take too much time to train them, or you might just not have the computing power to do it. You might have decreased performance, and if you don't know what variables are correlated with your target, you might have leaks. And I know what you're thinking, yeah, I'm smart, I will not have that, I know how to avoid that. Yes, I'm pretty sure you're very smart. I am relatively smart, and I was pretty sure that it would never happen to me, but it can happen to you. And you will not notice it. By the way, that's how data scientists look like when they're at work. That's a photo of me last week. So, as I mentioned, that happened to me. I had a very straightforward problem, a very well-defined target, popped everything into a machine learning model for classification, and boom, 99.9% accuracy. But then, if you have any experience in this field, after a couple of seconds, you should be like that. Wait, this is the first thing I try, no optimization, no data engineering, no feature engineering, no nothing. Something is wrong. And it turns out that something was wrong. One of the features actually had a bad leak from the target, and just removing that, made everything more general and, correct. Anyway, let's move on. As I mentioned, there are many ways that we can work on this type of problems, but we have to restrict the domain. We can't really talk about the highest systems in a talk of 30 minutes. So let's restrict it to a simple problem. Let's assume that we have a data set and a target, and we want to classify it. And full disclosure, this data set is actually a pretty well-known data set that I'm not going to tell you what it is for the moment. I'm going to tell you at the end. It contains 569 rows, 30 columns that I've helpfully named X00 to X29. And that's all we know about it. And this is going to be our problem for today, for this morning. So which of those features we choose? Are they all really important? And if some of them are not, how do we decide what is important and what is not? Well, there are many different techniques that we can use. There are many techniques also that are not so good. A lot of people will just go straight into descriptive statistics, use just correlation, for example, which is fine. But you shouldn't just use that, because descriptive statistics can be misleading. All of these data sets have the same exact summary statistics. And they're all quite different, especially like the Tyrannosaurus. So that's fine as a start, but you shouldn't just rely on that. You should use more aimed techniques. There are essentially three main categories of techniques that you can use for this. They go from very simple techniques to very complex techniques. And they can be grouped as follows. So there are filter techniques, which basically are univariate selection techniques, which can be essentially based on variance, like you have a feature that never changes. It has always the same values, or is always missing. Why keep it? It doesn't tell you anything. You have a feature that is completely correlated to another, like the correlation is 0.99. Why keep both? If you're using some algorithms that will actually throw everything off, it will kill your coefficients. You should consider dropping one. There are also techniques that are a bit more advanced, like wrapper methods. These, instead of looking at single univariate relationships, would look at how groups of features interact with each other towards a target. Like, for example, the classic, one of the most classic examples in this area would be feature selection by recursive elimination. Like, you take all of your features, you train your model, classification, regression, whatever. Then you remove one feature at a time and see if the model is still good. And then you remove the feature that actually is giving you the least problems there. And you keep going until you have a set of features that gives you the best possible result with the least number of features. And then there are even more advanced methods, which are embedded methods. They take a bit of both of the previous categories, And they also include some full-fledged machine learning models. Like, for example, this is what a random forest algorithm or an XGBoost or a decision tree would do. They basically select features based on how well they describe the dataset. And I can talk for hours about this, but I don't want to bore you too much. So if you want to know a few more details, just come find me later, and we can talk for hours. So, okay, fine. We have all these techniques. How do we use them? How do they help us? And how can we solve our problem? First of all, what was our problem again? We have a dragon to defeat. And I'm going to show you a bit of code here. As I mentioned earlier, this is not production-ready code. Don't use it. It's just here to give you an idea. I'm not even going to spend too much time on it, because it's the idea that matters, not just the code itself. So what we want to do is build a model that allows us to leverage multiple techniques to perform feature selection. And we don't just want to use one or two. We want to have an ensemble. We want to use many of these techniques, get the results of all of them, combine the results, and find the best features as identified by all of the algorithms. So we start easy. We need a few imports. We need a few techniques and a few algorithms. I'm not going to use too many because it's a slide deck. I can't really fit all of them here. But all of these algorithms have methods that can help you select features, like random forest classifier, decision trees. They all have feature importances, and that's what you can use. Variance threshold is essentially checking that features actually have variance in them. You set as a lower threshold. If the feature doesn't vary, it's not interesting. Then we need to define our problem. So different algorithms do different things, and some of them are great for regression, some of them are good for classification, some of them can do a bit of both, but most of them will only do one. So we have to separate the two cases. And we also want to have some others in case that we have a problem. We have a data set and we have no problem. Like, we only need to find out what's going on in there. We don't have a target. And as we have all of these, we need to initialize everything. We need to define how many features we want from each of these algorithms. We need to specify what type of problem we're trying to solve, if it's a regression, if it's a classification, if it's none of the two. And I also added a small thing for myself. I wanted to calculate overfitting, and there is no easy way to do that, but I found that, especially when you have imbalanced class, using the difference of the Matthews correlation coefficients works really well, reasonably well at least. And it can tell you if your generalization is good enough for what you're trying to do. Having the models, we need to set them up, instantiate them, save them somewhere, and keep track of them. And then we need to train them. It's very easy, just for all the models fit. And then this is the most important part. For each of those models, we need to get the feature importance. For some models, the ones that I'm using at least, it's easy enough. Some of them have the attribute feature importance, some of them have variances, some of them have scores. We get the appropriate variable, the appropriate attribute, and we store it somewhere. And then we have that, but how do we combine them? So to be completely accurate, you should need to add some sort of weighing, but I'm not going to do that here, because that would add an unnecessary layer of complexity to this presentation. So what I'm doing on this slide is essentially collecting all the scores for each algorithm and combining together. If a feature is identified as important from one algorithm, it gets a score of 1. If it's found important by 2 or more algorithms, it gets a score of 2, 3, or however many algorithms have picked it. And great, that's it. We're good to go. All right, it's done. It's not done. Come on, come on. I showed you some code. Does it work? Does it run? You'd be surprised at how much code I've seen, how many PRs that just don't even run. Let's see if it works. So let's get back to our problem. Remember what our data set was. We had this 500 something rows and 30 columns with these beautiful names. So what we do here is we generate our feature selector for classification, and we want to get 5 features from each model. We fit it, and we get the votes. And then I just print them. I need to find my cursor. Here we go. And, oh God. Here we go. So out of the 30 features, 9 features got votes from some of the algorithms. And just for completeness, I also added the scores at the bottom. So these were the 3 algorithms that were used. And these are the features with the relative scores. So yeah, great. It works. Satisfied? You should not. You've seen numbers. How does that compare with a real algorithm that uses all of the features? So what I'm doing here, I'm taking, well, it's a binary classification here, so I'm just using a logistic regression. And I'm training 2 models, one on all the features and one on only the ones that were identified by my feature selector. Let's see what we get. Bam. So actually, you see, using 9 features, our score improved. Not bad. Okay, fine. That's a fortuitous accident. In most cases, the score is slightly worse because I'm using random splits. In this specific case, it was slightly better, but it was always in the same range, plus or minus 1 or 2%. So it's quite impressive. We're using 1/3 of the features. We're using 1/3 of the data. Imagine that at scale. Imagine that instead of having 30, you had 10,000, 1,000,000, 1 billion. Using 1/3 of the features would actually improve your training time by a whole lot. And it will also probably improve your generalization, especially in that higher dimension. Are you more satisfied now? No? I see people shaking their heads. Why not? All right. In essence, what feature selection does for us, it simplifies the models considerably sometimes. It reduces training time. It allows us to dig into specific features that we deem more important than others. Avoids the curse of dimensionality sometimes, because that's a big problem, especially when you're trying to compare different points in a high-dimensional space, because that's a hard problem. Distances lose their meaning. It removes the noise, and it makes your job easier. So my suggestion is always try to reduce your data to the minimum that you need to solve your problem. And actually, that was a lot quicker than I expected. So I'm actually at the end of my presentation. So if you have any questions, I hope you have many. And I hope you're not completely satisfied by what I've shown you. Please go ahead.
One second, please. Okay. Who's? Okay.
Well, thank you very much for an interesting talk. Could you maybe lose a couple words on feature engineering? So what are your good tactics for combining them, calculating new ones?
Okay. So that could be the topic for a whole set of talks. There are many techniques to do some feature engineering. It strongly depends on what you're trying to achieve. One couple of techniques I usually tend to use, especially at first when I'm doing EDA, would definitely be PCA to help you combine some of the features, but PCA has the big problem of only considering linear relationships, which is fine in most situations, but sometimes you want to capture more complex relationships. Depending on whether you want to keep your understanding of what's going on or not, you might also consider autoencoders. Especially, that worked especially well for me when I was performing document classification. It was set of documents that was not even allowed to read, so it was just, how do I represent them in a way that I can actually manipulate? And also, it strongly depends on what kind of features you have. In some cases, you might have features that all work really well together, and they work even better when they are combined in some fashion. But it's, yeah, I would need a whole new talk to discuss that.
Okay.
Hi. So I just have one question for you to clarify the contribution or the difference in your talk. So the contribution that you want to bring is the combination of score from multiple algorithm, right? That's what I understand. Yeah. So you use 3 classifier, and then for each classifier you have a score for each feature, and then you combine them. Yeah.
Yeah, that's one way we use to cope with the problem. Yeah.
Yeah. So what about the result when you only use the features importance from one algorithm? Because here I see that you compare 30 features to 9 features that you have from 3 classifiers. So what about the 9 features from each algorithm? Maybe it will bring the same result. I mean, maybe it's not really necessary to combine multiple classifiers. That's my question.
That would depend on the data that you have. It might be, well, if these algorithms are internally quite different, they are looking at different things. They calculate importance or a score in different ways. So that's why I'm using an ensemble, because if you only use one algorithm, you're only looking at one particular facet of the whole problem, which might be perfectly enough. Like, if your goal is to reach, say, a score of 0.9, and with one algorithm you get to 0.91, you're done. You don't need an ensemble. But it's this was a very simplistic problem. In real big life data sets, you might have to use even more than 3. Actually, for a couple of our projects, we ended up using more than 10 to get to viable results.
Hello, thank you for the talk. My question is, the 9 features that were chosen by modules, they are chosen by each module, or it's the combine of different modules? So
in this case, it's the combination. If I remember correctly, in my example, I set each model to select 5 features. So each model gives me 5, and I combine them. Some of them get more than 1 vote, so that's why we get less than 15. But yeah, you end up with any number. In my case, you selected 5, so I will end up with any number between 5 and 15 with 3 models.
Hi, thank you for the talk. And my question is about, maybe I get it wrong, but basically what you do is you call, I don't know how many methods, and then classifiers, and then you, for example, you ask for a feature importance, right? Mm-hmm. Is that correct?
Yep.
And then you talked about scale. Like, I have, now I have 9 features, before I had 30. Mm-hmm. Imagine that you have 1 billion.
Yep.
But you're basically calling 9 classifiers.
That's true, but I wouldn't do that on the whole data set.
Okay.
Like,
but you're still using 1 billion features.
Yes, but imagine doing that on 100 rows or 100 billion rows. And it's clear to me that 100 over 100 billion is not a significant sample, but that's the point. you're still working on a fraction of the data, not on the whole. And then the new model, using only 1/3 or whatever fraction of the features, will probably have to be trained daily or weekly or every time it's needed or every time the performance goes below a certain threshold. So it's not just a one-time training.
But you still need to sample from your whole data, and then you okay, from the second time on, I get your we scale, but training like 9 or I don't know how many classifiers with a lot of features, I guess that running time there, it's pretty high. That's what I'm saying.
It could be, yeah. The sample that you use for that needs to be at least representative of the data that you have. But this is not something you would do right as a first thing. So you would first need to go do some EDA. So you probably ever dropped a significant amount of data. Like in our databases, which are quite well maintained, to be honest, every time I get a dump from a table, about 10% of the fields are just useless. So that's already a significant reduction with just doing nothing.
Okay, thank you.
Thank you for your talk. You talked about exploratory data analysis, classical machine learning algorithms, but jumping to neural networks, what do you think about the assertion that neural networks can substitute feature engineering?
I strongly disagree in most situations. It's true, neural networks do some feature engineering, but they mostly take away the understanding from you. And it's true, you can use attention, you can use a few other tricks to get some insight as to how the features were constructed. But ultimately, as a data scientist in a company, you're paid to understand what's going on and suggest courses of action. So it's one thing if you have as a final goal just, okay, I need to classify this into 1, 2, and 3. It's another thing if your goal is, I want to reduce customer churn.
If you want to have more questions, we have 15 minutes left. So actually 10. Okay.
That was the diabetes data set. Diabetes.
I just want to connect to the last question because depending on the process where the data is coming from, the initial data set, it's also the collection, the way you collect that data, and if it's any kind of process, even the data coming from transaction, from e-commerce websites, we need to assess many things. I just think among many things that the ergodicity of the process, we don't know from the beginning, and if we can find a way to maybe to collect the samples in some uniform way, because otherwise the feature extraction will be skewed by the. I just wanted to comment on this to have, and I wanted to know what do you think about it. There is, I would say that there are some step forwards on the feature extraction, but there is still some work to do on the sampling and collection of the initial data. That there is lots of room for improvement there.
Oh yeah, of course. I mean, my talk assumes that we already have a data set that's reasonably well collected. But if you don't spend a lot of time making sure that the data you collect are at least at an acceptable level, then whatever you use for any analysis or classification or whatever algorithm or problem you're trying to solve, then it won't be great. It's like the whole principle of garbage in, garbage out.
Okay, better. As I understood, you're using different classifiers, and each of these algorithms have a set of parameters to set their behavior. So how can you know how to set these parameters? I mean, what if one of the classifier is not doing its job? It's not classifying correctly. So how can you understand that from the last step, from the voting? How can you know if you are getting a bad result? It's because one of the classifier is failing, for example.
That's a very good question, actually, and it's something that I didn't think of telling you because it just didn't fit on the slides, so I just forgot about it. But in the library that we have, that we're actually using in production, we do have a threshold, a minimum threshold for both F1 score or Matthews correlation score, depending on how classes are imbalanced, and an overfitting score. And if a model doesn't perform well according to those two scores, we just don't consider the results. But yeah, it's something that should be kept in mind, because if a model is not doing its job, like a model could be 99% of the times correct, only classifying everything as 0 in a binary classification, but that's not useful at all. It's something that you should always take care of avoiding. Yeah, you can only reliably use classifiers that are performing reasonably well. The reasonably well will depend on your problem and your data.
Thank you for your talk. I just have one question here. I just have one question about the type of the data you're treating. So in this particular case, I've seen that there are all numerical data. And I was wondering whether using dealing with the categorical data can have a different result. Just to know, maybe if you have a categorical variable that have maybe 2, 3, 4 possible values, just one hot encoding may work. But when I had cases when I had maybe one variable with 300 or 400 possible values, and then the noise is heavily increasing. Can this kind of approach be used also for that kind of data? Thanks.
Well, yes, in short. There are many approaches you can use for that. And personally, I have used one-hot encoding up to a few thousand values per variable. I wouldn't recommend it, but it can work. There are algorithms that deal with categorical data pretty well. For example, especially if you're going to perform classification or regression, CatBoost does that reasonably well. There are other techniques, especially if you have a lot of unique values, like using the hash trick. That can work. It gives you back numerical data again. You have to be careful about treating it, because you might, it's a hash, so it's unlikely, but you might introduce correlations that don't really exist because it's numerical, although it's a hash, so I'd be surprised. Those would be the main two things that come to mind, mostly tuning the algorithms you use, or transforming the data in a format that your algorithms can deal with. Okay, I guess I don't see anyone else. So
anyone else? So I think
thank you all guys for
yes.
Thank you all guys.
Thank
for coming
you.
here.